In this video, we will continue our study on binary search. Okay, so first, let's recall what binary search is. Well, we know that binary search is a search algorithm that we can perform on sorted arrays. And essentially the idea is that we can check the middle element of our search range. And if our target is less than this middle element, our search range can become the left half. And if our target is greater than our middle element, our search range becomes the right half. And then finally, otherwise, we have found our target. And so now the question is, what have we not learned about binary search? Well, it turns out that we can use binary search on things other than arrays. In fact, we primarily binary search on either arrays or functions. And yes, functions like f of x. Okay, so what is an example of a function f of x that we can perform binary search on? Well, one example would be one of the subproblems from DMOPC 2016 November zeros, and it essentially asks us what is the first factorial that contains at least n trailing zeros. So in this case, what would f of x represent? Well, f of x represents the number of trailing zeros x factorial has. Now, although we know that we can binary search on sorted arrays, what is the criteria for binary searching on functions? Well, the primary requirement for a function f of x to be binary searchable is that f of x is monotonic. So that means f of x is either non-increasing or non-decreasing. Or in even simpler terms, for every I, f of I is less than or equal to f of I plus 1, or f of I is greater than or equal to f of I plus 1. So as you can see on the right here, the function that's in the blue, is monotonic because it's either increasing or staying the same. But the red function, as you can see, has some parts that are increasing and some parts that are decreasing or some parts that are staying the same. And so that's why we call it non-monotonic. Before we move on, let's talk about the lower bound function. So essentially, the lower bound binary search method or function should return the first x such that f of x does not compare less than the target. So in other words, the first element greater or equal to the target. So in this example here, essentially if we perform the lower bound function where our target is 20, the lower bound should return 7. And so once again, this returns the first x such that f of x does not compare less than the target. So it returns the index of the first element greater or equal to the target. So in this case, our target is 20. The first number greater or equal to the target is 21. If this list included a 20, then it would return the index of that 20. Okay, so here I've provided the lower bound pseudocode in which you need a low, high, and a target. So what we're going to have is the low is starting at 0, and our high will start at n. So that's going to be our entire search range. Then we're going to say while the low is less than the high, we're going to calculate the middle by saying low plus high divided by 2. And then if we pass that middle number into our function and see that it's greater than or equal to our target, then we'll set our high to the middle value so that we look on the left side. And if our f of mid is less than the target, we know that it's less than our target, right? Then we want to change our search range to the right side. And until that's done, essentially what we're going to do at the very end is print this low here. And then we found our lower bound. The same idea applies to something called the upper bound. And essentially, the upper bound binary search method or function should return the first x such that f of x is strictly greater than the target. So this is not less than or equal to the target. So essentially what that means is it's the first number greater than our target. So if we look at this list here, if we essentially have these numbers 1, 3, 6, 8, 9, 15, 19, 20, 38, 68, 92, and we perform the upper bound, on this array with a target being 20, the return or the upper bound would not return 7 here because that value is not strictly greater than our target. The first value that is greater than our target is this 38, and so the upper bound would return an 8. So it returns the first x such that f of x is strictly greater than our target, or in other words, the first number greater than our target. Okay, so here I've provided some upper bound pseudocode in which it looks very similar to the previous code, but the very only small minute difference that you'll see between upper bound and lower bound is this inequality right here. For lower bound, this inequality is actually greater than or equal to, while in upper bound, it's actually just simply greater than. So this is the first, you're just going to pass in f of mid and check whether or not that value is greater than our target. And so that's the pseudocode for upper bound. Okay, so now that we've seen upper bound and lower bound, let's also look at some out of bounds tips. So suppose all your values of f of x are less than our target value. So for example, if our target was 20 and all the values in our function were 1. Well, after a binary search, low will be equal to our initial high value. And so the question is, can we check f of low if f of low is less than our target value without computing f of low? Well, the idea is to set the initial high value to 1 more than the highest value. So for example, we would do instead of n, we would do n plus 1. And so the idea here is that the initial high value is known to be an invalid answer, right? We'll never get to n plus 1. And so the initial high value will never be used to compute the answer. So the reason for that being is because high will never increase. And when low is less than high, mid will always be less than high. And when low is equal to high, the binary search is finished. So to check if all values of f of x are less than our target value, simply check if low is equal to the initial high after the binary search. And that will tell you whether or not all values of f of x are less than our target value. Now, with those out of bound tips, we also have some alternate mid calculations. So some sources tell you to use mid is equal to low plus high minus low divided by 2, instead of mid is equal to low plus high divided by 2. So the reason we do this is due to the potential overflow or the integer overflow error of the second version. So usually integer overflow error is not common unless the limits of high approach your data type limit. So like integer is 2 to the 32 minus 1. And the reason for that being is since during computation of mid, low can be equal to high minus 1. Overflow can happen if high is greater than or equal to the limit divided by 2. And so if you do high plus a high minus 1, then it will overflow your limit, right? But both versions will produce the same values otherwise. Okay, so now going back to the binary search example of zeros, the overall problem is what is the first factorial that contains at least n trailing zeros? So in this case, what would our f of x represent? Well, f of x represents the number of trailing zeros x factorial has. So then the question becomes, how can we compute f of x? Well, we should note that we have an additional trailing zero for each factor of 10 we can form. And since 10 is equal to 2 times 5, and 2 appears as a factor more often, we want to count the number of 5s that appear as a factor from 1 to x. Thus, we can say f of x is equal to the sum from I is equal to 1 to infinity of the floor of x divided by 5 to the I. So as a quick explanation of why f of x is equal to the sum from I is equal to 1 to infinity of the floor of x divided by 5 to the I, we can think about it in this way. If we only have the numbers 1 to 11, we can simply do 11 divided by 5, and that'll give us the number of 5s that appear from 1 to 11. So that's just the 5 that is contained right here, and the 5 that's contained in here. But as we see with larger numbers from 1 to 25, if we simply do 25 divided by 5, we only get 5. And that's actually incorrect. So the answer for this one should actually be 6, because there are 6 times that 5 appear from 1 to 25. And so that's from 5 is equal to 1 times 5, 10 is equal to 2 times 5, 15 is equal to 3 times 5, 20 is equal to 4 times 5. But with 25, it's a factor of 2 5s actually. So we're missing one of the 5s for 25. And this can be extended to larger numbers. So for 125, this would actually be 5 times 5 times 5. And so once again, if we only divide 125 by 5, we're undercounting the number of 5s that exist. So we also need to count the number of factors of 25. That'll give us the factors that are containing 2 5s, then 125, and then so on. And we can stop when this number that we're dividing by, this power of 5 that we're dividing by, is greater than the value of x, because that'll just give you 0. And so for the binary search example of zeros, once again, we can use the lower bound method to find the first value of x such that f of x is at least n. So for example, if n is equal to 10, we can start our search range at low is equal to 1, high is equal to 100. Mid is equal to 1 plus 100 divided by 2, which is 50. Check f of 50, so we get 10 plus 2 from that, which is equal to 12, which is greater than or equal to 10. Then we're going to set high to equal to mid, which is equal to 50. Now that we've reduced the search range to the left side, because our function returned a value greater than our target, what we're going to do is we're going to set the high is equal to mid is equal to 50, and so we're going to recalculate the middle again. So the mid is equal to 1 plus 50 divided by 2, which gives me 25. F of 25, the number of trailing zeros for 25, is equal to 5 plus 1, which is equal to 6, which is less than 10. And so low is equal to mid plus 1, which is equal to 26. We want to look on the right side now. Now that we're looking on the right side, recalculate the middle. So mid is equal to 26 plus 50 divided by 2, which is equal to 38. The number of trailing zeros for 38 is equal to 7 plus 1, which is equal to 8, which is less than 10. So because our target value is 10 and 8 is less than 10, we need to look on the right side again. So low is equal to mid plus 1, which is equal to 39. Then what we're going to do is we're going to look on the right side, recalculate the middle. So mid is equal to 39 plus 50 divided by 2, which is equal to 44. The number of trailing zeros for 44 is equal to 8 plus 1, which is equal to 9, which is less than 10. So we need to once again look on the right side. Low is equal to mid plus 1, which is equal to 45. Now that we're looking on the right side, we can once again recalculate the middle, which is equal to 45 plus 50 divided by 2, giving us 47. The number of trailing zeros for 47 is equal to 9 plus 10, which is 10, which is less than or equal to 10. And so now we can look on the left side. Now that we're looking on the left side, mid once again is 45 plus 47 divided by 2, giving us 46. The number of trailing zeros for 46 is 10, which is less than or equal to 10. Look on the left side again. And then finally, mid is equal to 45 plus 46 divided by 2, which gives us 45. F of 45 is equal to 9 plus 10, which is equal to 10, which is also less than or equal to 10. And then finally, since low is equal to high, the answer is 45. Now let's analyze the binary search analysis. So the binary search itself is O log of n. And at each step of the binary search, we need to run our function f of x, which has a time complexity of O of g of x, where g of x is some other function. The true time complexity to compute f of x depends on the nature of the function. And so the total time complexity is O of g of x times log of n. Okay, so now let's actually look at the problem itself. So the problem states, recall that the factorial function is defined as the following. So n factorial is equal to n times n minus 1 times n minus 2 all the way to 1. And so the problem states, given integers a and b, please find the number of natural numbers n such that n factorial has a number of trailing zeros in the range of a and b. Okay, so in this example, we want the number of trailing zeros between 0 and 2. So in this case, we should get 14. And as you can see, n factorial is equal to 1. So is the first element that satisfies the condition. And 14 factorial is equal to this number is the last element that satisfies the condition. So hence there's a total of 14 values of n that satisfies the condition in this case. Okay, so once again, we've kind of already outlined how to do this problem, but essentially the way we could do it is take what is the first value that is greater than or equal to 0, that has greater than or equal to 0 trailing zeros. And then for this one, for the upper bound, we're actually going to look for the first number that has greater than b zeros. So we actually want to include all of b. So we're going to skip all of b, the numbers with b trailing zeros, and we're going to look for the one with b plus 1 trailing zeros to include all the ones with b. Okay, so first what we're going to do is we're going to take in input for our numbers. So the first number that we're going to take input for is the two long numbers, so here and here. And the reason we're going to use long for them is although they fit into 10 to the 9, which is an integer, we're going to be using arithmetic using long. So long A is equal to read long, and long B is equal to read long as well. From there, I'm actually going to initialize all the power of 5s. So essentially here, what we can do is create an array of longs actually. And what this is going to be is this is just going to be an array that contains all the powers of 5s. So we're going to say pows is equal to new long of size 30, for example. And what we're going to do is we're going to compute the first 25 or so powers of 5, or base 5s of some power, right? This is going to be 5 to the power of I, where I is some number, right? And so the way we can do that is simply by saying pows 0, right? 5 to the power of 0 is equal to 1. And every time we go through each of the numbers, it's just the previous one times 5. So we can say pows I is equal to pows I minus 1 times 5. And there we go. So this might be a long to make sure that it is a long. Okay, so next what we're going to do is we need to find the first index or the lower bound of A, right? So let's actually store some variable called it A, for example, and this will be the lower bound of A. So we're going to find the lower bound, so the first number that has greater than or equal to A trailing zeros. So we'll make that function later. We're going to do the exact same thing for B, but this time we actually want to find the upper bound of B, right? So the reason we want to find the upper bound is because we want to include all the numbers that contain B trailing zeros, right? And in the end, what we're going to do is we're just going to subtract their indices, and we're just going to essentially find the number of trailing zeros between that range. Okay, so the first thing that we're going to do is we're going to create a function. And this is going to give us the number of trailing zeros. So let's say trailing zeros of some long n. And essentially what we're going to do is we're going to create a counter, and we're just going to keep dividing them and then summing them until we found the correct number of trailing zeros. So what we can say is if pos I is greater than n, right, then we can just stop there. We can stop there because if we keep dividing it by a larger number, so if pos I is greater than n, then our result will just become 0, right? And so we can stop there because we know that we no longer need to divide it. Otherwise, we know that count will add n divided by pos I, right? So just like that. And that'll give us the sum, right? That's the formula that I showed you guys earlier. Then all we have to do is return the count. This is going to give us the number of trailing zeros for an integer n. Then all we have to do now is find the lower bound of a, right? So let's create that function. And we're going to pass in an integer x, for example. And what we're going to do is we're going to start our search range at 0. And we're going to end it off at some really big number, like pos 25. From there, we'll just use our classic lower bound code while low is smaller than high. Let's create that mid value. So that's going to be low plus high divided by 2. And if f of mid, or the number of trailing zeros for my mid value, is greater than or equal to x, right, then high is equal to mid. And otherwise, low is equal to mid plus 1. From there, all we have to do is return low. We can do the exact same thing for our upper bound, and all we have to do is change this right here. So in fact, I'll copy this code, change this to upper bound, and change this to simply greater than. Okay, so from there, all we have to do is we need to print out the number of numbers that have A trailing zeros to B trailing zeros, right? The number of trailing zeros is monotonic, so that's why we can do binary search on it. Okay. So if this actually gives us 0, so if the lower bound here gives me 0, so this is the first number that gives me that it has A trailing zeros, and if that value is actually 0, then this will give me the correct answer. So in fact, I need to reset A to equal to 1. So this is a bit of an edge case for this problem. Then finally, all I have to do is print it B minus it A. And then that'll give me the correct answer. So let's run it. And we seem to have some kind of error. Let's see. So yeah, we need to actually set these to longs. And there we go. Oh, that's right. We need to create these methods as static. And there we go. So we get correct for the sample input. So let's submit this in Java 8. And as you can see, we get all correct answers. So in this video, you learned about binary search and its more advanced concepts, and we showed you how to perform binary search on this problem called zeros.